Hello, good evening, everyone. Sorry for the delay. I lost the slides I prepared, so I was remaking them. I have successfully compiled it, so we will start now. Thank you for your patience and all that. I'll make the lesson worth your while, and we'll try to cover exactly what we were supposed to cover in the given time. Hopefully, the lesson will be helpful. We begin now. Okay, so before I begin, I can be clearly heard. Please let me know if I can be clearly heard. So I assume I cannot be heard then. Oh, okay, yeah, all right. Thank you, Mr. Freeman. Okay, then we proceed. And also, let me confirm, can you see what I'm sharing on my screen? And if you can, what exactly do you see? Okay, all right. Thank you, Mr. Freeman. Then we proceed. So in yesterday's lesson, we discussed probabilities, and we mentioned that conditional probabilities calculates the possibility of an event happening, given that another has happened, where the preconditioned event becomes the sample space. And we looked at a few examples on that. Are there any questions concerning that lesson before we move on to total probability? Okay, so before we proceed, I'd like to say that the lecturer spoke to us concerning the sector or the parts of his slides where he'll be setting his questions from. And when he did, he mentioned two concepts, total probability as well as Bayes' theorem. And these two concepts are underlined, like they are built upon from conditional probability. So do not worry. Our workings so far have been in accordance with what the lecturer said he will prepare. Also, I have questions from our previous tests and then some courtesy of Madam Vida that we will have to that we can work. However, looking at the nature of the questions, I can say that they are the ones that we have treated and understand, and then they are the ones that we have not yet treated. So for that reason, we will not be able to work. Therefore, I take my time to go through the questions and then pick out the ones that we have treated and then rephrase them. The very same thing, sometimes rephrase and sometimes set similar ones. Also do same for the slides. And then I inject them into my slides. So yes, don't worry. When we are working the examples here, we are actually working ones that mirror the very same ones that we have treated in the test and whatnot. So do not worry about the fact that there are test questions to solve that we are not solving. We actually are. All right. So here's a recap on our previous lesson yesterday. The conditional probability is the chance that an event happens given that another event has already happened. Example, if it is raining, then the probability that you carry an umbrella increases. So the chance depends on the condition rain. Notation, so it is written as the probability of A given B, like so, which means the probability of A given B has happened. Why conditional probability matters? So in decision making, conditional probability helps us make better decisions by considering extra information. So for example, in a medical test, what is the chance that you are ill if the test is positive? What this means is that sometimes in a test, the device or the tools being used for the testing could actually sometimes in rare scenarios measure you positive, but then actually you might be negative. So it means that there is a chance that the positive test is correct and there's a chance that the positive test is wrong. So as a medical personnel, you should be able to ascertain the fact that my test might be truly positive and no, or maybe falsely positive. You can only do this by knowing conditional probabilities. Now the weather too, what is the chance of rain if the clouds are dark? So if the clouds are dark, the chances of rain increase. Doesn't necessarily mean that there's 100% chance of rain. You can attest to that fact. However, it increases the chances of rain. Real life scenarios include in a business, what is the chance a customer buys again, given that they bought it last month? Or education, what's the chance that a student passes, given that they all attended classes? Conditional probabilities everywhere in daily life. Now to today's main session or main lesson, total probability. So the total probability rule helps us find the chance of an event by considering all possible ways it can happen, especially when one way depends on different conditions. I'll take that again. It helps us find the chance of an event by considering all possible ways it can happen, especially when each way depends on different conditions. It is useful when an event can occur in several different scenarios, each with its own probability. Here's what this means, okay? Let's say you are told that in a given room, there are shoes in there. So let me draw my room. Now let me use a different color so we can see. So let's say we are told that in a given room, there are shoes in there. And then the shoes are in 3 different boxes. So maybe the entirety of this is the room, right? And then let's say I am going to use this sphere here to represent the shoes. So the circle in the middle is the shoes. Please keep that in mind, okay? And then I tell you that there are 3 different boxes and each one contains shoes. So let's say this is box 1 and box 1 contains some shoes. So let's say the shoe is S. So let me say these are the shoes in box 1. And then this is box 2 in the middle here, like so. And box 2 also contains some shoes. And then this is also box 3. And box 3 also contains some shoes. And please, the publicity team, can you please inform the people in the platform that the session has begun so they can join in now? Thank you. All right. So now, if I ask you, how many shoes are in the room, right? Your question is, how many shoes are in the room? Your answer will be the number of shoes that can be found in every single box in the room put together. This will mean that I will have to add the shoes from box 1 plus the shoes from box 2 plus the shoes from box 3. Putting that together is what gives me the number of shoes in the room. I hope this makes sense, right? Now, let's rephrase the question. What is the probability of picking a shoe from the room? So if I ask you, what is the probability of picking a shoe from the room? This time, I'm not just asking the number of shoes, but what's the probability of picking a single shoe from the room? I'm not specifying whether it's coming from box 1 or box 2 or box 3. I just want the probability of picking one shoe from the room. This will mean that the shoe can come from box 1. It may come from box 2. It may also come from box 3. Therefore, in order to know the probability of picking a shoe from the room, I have to know the probability of picking it from box 1, add that to the probability of picking it from box 2, and add that to the probability of picking it from box 3. Combining the probabilities of picking shoes from all the different boxes gives us the combined probability of picking a shoe at all. This is known as the total probability rule. So basically, the total probability rule combines all the separate ways a particular event can happen. That's all there is to it. I'll take my explanation again. Suppose you are in a room and then the room has shoes. These shoes have been sorted into 3 boxes. Box 1, box 2, box 3. The shoes all put together is a particular number of shoes, like it's just shoes. If I ask you how many shoes are in the room, what you will do is you will add the shoes in box 1 to the shoes in box 2 and add that to the shoes in box 3. That's simple. If I ask you, what's the probability of picking a shoe? Since there are 3 separate boxes, you do not know whether the shoe comes from box 1, box 2, or 3. Therefore, you have to consider the fact that the shoe may come from any box. So you have to find the probability of the shoe coming from box 1, add that to the probability of it coming from box 2, and add that to the probability of it coming from box 3. This together will give you the probability of picking a shoe at all. So now let's go back to what we learned yesterday about independent scenarios. We mentioned that independent scenarios are scenarios that the occurrence of one doesn't affect the occurrence of the other. Now, this particular one here, if we decide to pick a shoe and we want to know the probability of picking a shoe, we are going to first have to see. So let's define the probability of picking a shoe at all as probability. Oh, I think red is not clear this on this. Let me use black. So probability of picking a shoe should be defined as probability of S, right? So if I want to pick a shoe, this will mean that I have to first know the probability of picking a shoe from box 1. And that is going to be the probability of me picking a shoe from box 1. That's probability of the shoe coming from box 1. So B1 intersection S1. It means I'm picking the shoe, and the shoe should also come from box 1. Added to the probability of me picking the shoe from box 2. That's going to be B2 and S2. And finally, add that to the probability of me picking it from box 3. And that's going to be B3 and H and S3. So what does this mean? In order for me to calculate the probability of picking a shoe, I have to find the probability of the shoe coming from box 1 or probability of it coming from box 2 or probability of it coming from box 3. And we mentioned yesterday or earlier in our earlier lessons that probability OR is mostly for additions. So we have to find probability of it happening in box 1 plus probability of it happening in box 2 plus probability of it happening in box 3. Now, mostly, this is the formula actually for the probability, the total probability rule. So it combines all the probability for all events, and that gives you what we are looking at here. Now, mostly in the questions that are given for total probability, the intersections for both probabilities are not given. You see the n we are using here, they are not given mostly for these questions. Therefore, we have to figure out what the n's are. Now, remember when we were learning conditional probabilities, the first lesson, I mentioned that there are 2 ways the conditional probability formula can be expressed. The first one was what we have looked at. That's the probability of an event A given B is equal to the probability of the intersection of A and B. That's what we looked at yesterday. All over the precondition, which is B, so probability of B. Like so. Now I told you that inversely, this formula can be expressed when we are looking for the intersection here. We may rewrite this formula as we do some change of subjects, and this guy multiplies this over here. So then the whole formula now becomes, use a different color because I can't see. All right. The whole formula now becomes the probability of A intersection B is equal to the probability of B times the probability of, so times the probability of A giving B. This is from our first lesson, and this is just change of subject, by the way. What this means is that if we are not given the intersection, but we are given the other parameters like the probability of B and also the probability of A giving B, then we can find the intersection by just multiplying the probability of B and the probability of A giving B. Now, the total probability formula is actually expressed in these terms. So instead of writing B1 intersection S1, like you can see here, what it is going to do is it will rather write it as the probability of B1 times the probability of B1 given S1. So it's going to express the intersections using the reverse formula like this. And that's the total probability rule. So then either way, you can state it like this, or you can state it like this by combining every single probability of A intersection B, by instead writing it as this. So this is what I'm implying. So instead of writing probability of B intersection S1, you may write it as the probability of B1 times probability of B1 given S1. The probability of B1 given S1 for the first box. So the intersection can be expressed as this right here. And then you combine that with what is possible to happen in the second box. That will be the probability of B2 times the probability of B2 given S1. AS2, yeah, like that. And then you keep doing that all for the third until the third one, and that will give you what the probability of picking a shoe at all will be. So then this one here is to explain what the formula looks like. Just like yesterday's lesson, we are going to understand the formula. When we are done, we're going to do some examples, and you also try some more. So before I move on to the next slide, are there any questions that you have pertaining to what I have just done, so that we do not carry it on to the next page? If you have, please feel free to ask, and it will be dealt with. Okay, so since no questions were asked, I will assume that everybody fully grasped the concept, so then we can move on, right? Or have the mics been muted? Let me check.
No, we can speak.
Okay. Okay. So is it that it's clearly understood, or the questions are hiding themselves?
I think it's clearly understood.
Oh, okay. All right. Thank you for that. Thank you for that. Now we move on to the next slide. So now this is the formula for the total probability generally. Okay. So what we just looked at on the previous page, it says that in order to calculate total probability, you will have to take the probability of each event, for example, event H1, and multiply it by the probability of an event given that event, like in what I explained from the previous slide. So it's basically probability of A intersection H1. But you know, A intersection H1 can be written as H1 times probability of A given H1. So now the sum, or the summation symbol you are seeing here, tells you that we will be dealing with several different events or different probabilities. Therefore, to find the total probability, just find each event's intersection and then add them together, like what I expressed in the first slide right here. So then you see it says this, what you can see here, probability of B1 times B1 giving S1 plus probability of B2 times B2 giving S1. And this will be written as the sum of the probability of all B's times every B given S. And that's what you can see here. So the sum of the probability of all H times the probability of all A's given H. So it says probability of A is equal to the sum of probability of A given B1 times probability of B1. That's the same thing written up here. And then it says the sum of probabilities across all cases. And when do you use it? When an event can happen in several different ways, like in the case of the shoes in the box, where the probability of picking a shoe can be with respect to first box or second box or third box. Then you apply the total probability formula so that we can find the probability of it happening in any given box, taking each box into account. And each way has its own probability. Here's the first example we'll be looking at. And just like yesterday, on each page, I'll be putting the formula there so that we can easily use it for the working. Now, it says you randomly pick one of two bags. Bag 1, B1, chosen with a probability of 0.6. Bag 2, which is B2, with a probability of 0.4. The probability of drawing a red ball from bag 1 is 0.5. And the probability of drawing a red ball from bag 2 is 0.25. Find the probability of drawing a red ball at all. Let's take the question again. You randomly pick one of two bags. Bag 1 is chosen with a probability of 0.6. It means you are randomly picking a bag. It could be that you're picking bag 1 or bag 2. We don't know. But we know that the chance of you picking bag 1 is 0.6. And the chance of you picking bag 2 is 0.4. So now, after picking the bags, we said that you picked a red ball. Now, when picking the red ball, we do not know whether you're picking it from bag 1 or bag 2. But we are saying that the probability of you picking the red ball from bag 1 is 0.5, and the probability of you picking the red ball from bag 2 is 0.25. So now we are finding the probability that you are picking a red ball at all. So let's assume there are other balls in the bag, and we are trying to pick a red ball. So let's find the probability of picking a red ball at all. Let's look at the formula that says is the sum of all given events and all given intersection of probabilities. Okay, a quick question. When I hit annotate, right, do you see the panel of colors that are displayed on the right side of the screen? Does that make does it make it hard for you to see the slides? If yes, tell me so that I can use a different method for the annotations.
Oh,
Was that a no?
But I think this one is good than the.
yeah, that's my side.
So I should maintain this.
Yeah, if you maintain this, it will be good. But because that's a
All
danger.
right. All right. All right. Okay. Let's work then. Okay, so let's do the working for this. Remember, we are trying to find the probability of picking a red ball at all. The probability of picking a red ball means we may pick a red ball from bag 1 or we may pick a red ball from bag 2. So in order to find the probability of picking a red ball, we need to find it coming from bag 1, then add that to it coming from bag 2, since it's either bag 1 or bag 2, not bag 1 and bag 2. So now, what would the probability of the ball coming from bag 1 be? So we know it says that when we take the chance of picking bag 1 is 0.6, and then the probability of picking a ball from bag 1 is 0.5. So then according to the formula, we have the probability of bag 1 as the HI you see here, and the probability of picking a ball from bag 1. So in other words, the probability of picking a ball, given that you took it from bag 1. That is what has been told or has been said here to be 0.5. Therefore, if we are even supposed to, or if we are going to state the formula, we are going to say that the probability of picking a red ball, which is we will write as P of R, okay, is equal to the probability of picking a red ball from bag 1, which will be giving us the probability of picking bag 1 times the probability of picking a red ball, given that it comes from, or given that you picked bag 1, like so. Good. And we need to add that to the probability that we pick bag 2. And the probability, we multiply that by the probability of picking a red ball, given that we picked bag 2. So red, given that we picked bag 2, like so. Combining these two probabilities is what will give us the probability of picking a red at all that you can see here. So now let's identify all these parameters and put them in the question. Let's start with the first part of it, probability of picking bag 1 times the probability of picking a red ball from bag 1. So that's going to be probability of picking bag 1 is 0.6, right? So 0.6. And we are multiplying that by the probability of picking a red ball from bag 1, which has been given to be what? 0.5, like this. And then we add that to the probability of picking the red ball, but this time from bag 2, which is said to be probability of bag 2 times probability of a red ball from bag 2. So the probability of bag 2 is 0.25. And we are multiplying that by the probability of picking a red ball from bag 2. Sorry, the probability of bag 2 is not 0.25, it's rather was 0.4. Good, 0.4. Okay. And we are supposed to multiply that by the probability of picking a red ball from bag 2, which is 0.25. So let me just do that. 0.4 times 0.25 or 0.25 times 0.4, right? They are still the same thing. Multiplication is commutative. So then we do these two multiplications, and summing them up is what is going to give us the total probability of a red ball being picked. So red ball from bag 1 plus red ball from bag 2, basically. So now, please pound this on the calculator. 0.6 times 0.5, what does that give us? Is it 0.30?
0.3. Yeah.
0.3, thank you. So 0.3, that's the probability of picking a red ball. Now we add that to the probability of picking a red ball from bag 1. Now we add that to the probability of picking a red ball from bag 2, which is 0.25 times 0.4, which is what, 0.1?
Yeah, 0.1.
All right, 0.1. So 25 times 4 is 100, so there's 0.1, as you can see here. So combining these two will now give us the probability of picking a red ball at all, which is exactly 0.4. Am I right?
Yeah.
0.4. Excellent. So then you can see this working clearly details the fact that if we ask you to pick a red ball, we are not specifying whether it's coming from bag 1 or bag 2. Therefore, you cannot just get up and say, I'm picking it from bag 1, I'm picking it from bag 2. You must consider the fact that it may be coming from bag 1 or it may be coming from bag 2. Therefore, your probability of picking a red ball should be the sum of it coming from a bag 1 and it coming from a bag 2. That's basically what this means. So for every question that will be given, this is the formula that we are going to apply. Are there any questions? All right, so since there are no questions, I believe we can proceed. So the next question we look at, it says 2 shifts and defective items. There are 2 factories. Factory S1 produces 70% of items with a 2% defect rate. And factory S2 produces 30% of items with a 5% defect rate. The two of them produce products. What is the overall probability that a random item picked from a random company is defective? So 2 factories, factories S1 and factory S2 are producing items. Factory S1 produces 70% of items with a 2% defect rate, whereas S2 produces 30% of the items with a 5% defect rate. If both of them do their production and we pick a random item, what is the overall probability that it is defective? This means that the probability of it being defective, let's write that as the probability of D, right? So probability of being defective, D, is going to be the probability of it being defective coming from machine factory 1, right? In other words, D intersection F1 or S1 in this case. So the production of probability of taking a defective product coming from S1 will be the probability of picking S1 at all, right? We look at the probability of it being defective coming from factory 1. And that is not all. We also consider the probability of it being defective coming from factory 2. So we add probability of being defective coming from 2, which will be written as S2 times probability of being defective from factory 2. D given S2, like this. So now combining these two is what gives us the probability of picking a defective product. So now let's do that. From factory S1, the probability or the production from S1 is 70% of product. This means the probability of picking an object that was produced in factory S1 is 70%. Therefore, probability of picking S1 is 70%. Let's express 70%. Remember, 70% and then 30% are representing probabilities of picking goods from either factory 1 or factory 2. This means the total, assuming the total amount of good produced is 100, 70 will be coming from factory 1. So the probability of picking a good from factory 1 is going to be 70 over the total, which will be 100. In other words, 70%. And as a decimal, that will be written as 0.07, right? So the probability of picking a good from factory 1 is going to be 70% or 0.7. We multiply that by the probability of picking a defective item, given that it comes from factory 1. And then it says that factory 1 produces 2% defective items. 2% can be also written as 0.02, like so. We add this to the probability of picking the defective items, but this time picking is from factory 2. So the probability of picking an item from factory 2 at all is 30%. So that's 0.3, like this. And we multiply that by the probability of picking a defective item, given that you picked factory 2. And that is 5%, which is the same as 0.05. So please punch these values on your calculator first. And let's see. So what's 0.07 times 0.02?
0.014.
0.014. Thank you. And then,
14.
yeah, 14. And then the probability of 0.3 times 0.05 will be what? 0.015. Or am I wrong?
0.015.
0.015. So then adding these two together, what does it give us? The probability of defective. So now we've calculated it for given that it comes from both sides. So that's going to be what? 0.029. 0.029. So this, ladies and gentlemen, is what the total probability rule is all about. And it just states that given that an event can happen in different ways, a particular event can happen in different ways with different probabilities, then the probability of that event happening at all is going to be the sum of it happening in all different ways put together. That's all. Before we move on, are there questions or would you like me to go over the working? Just say so and it will be addressed. Okay, I like today's session. Looks like oh yeah, Mr. Felix Freeman, please go ahead.
Good evening.
Good
I
evening,
would like
boss.
to ask, because of the nature of the question, as in the data being given in percentage, can you leave your answer also in that nature?
Yes, please, you can leave your answer as a percentage. So then
Thank
I'll go back to our first few lessons. When it comes to probability, there is no strict way to leave your answer unless the question specifies that you do, right? However, for some instances, it's more appropriate to leave it as a percentage, but leaving it as a decimal is still not wrong. I hope that's clearly understood. But if the question specifically, says that do it this way, then you must do it that way. The only catch is that probabilities must always be left in their simplest forms. And a decimal will always give you the simplest form of its equivalent fractions. So every equivalent fraction will have the same decimal representation. So whether you leave it as a percentage or decimal, I think both are fine. So let's express this as a percentage. What would that be? So this will be what? Is that 0.29,
2.9.
then 2.9 exactly. So then the point jumps forward twice, and that will be 2.9%. This means there is a 2.9% chance that the defective an item picked from any of the factories is defective. All right. Thank you for that question, Mr. Freeman. So remember, you may choose to leave it as a decimal percentage, but as he said, you see the way the question gave every single parameter in percentages, it is more advisable to leave it as a percentage, and I totally agree with him. Let's move on. So now, this time, I will leave it to you to try. 3 suppliers supply parts B1, 40%, B2, 35%, B3, 25%, with the probability that a part is faulty if it's from B1 as 0.01, or if it's from B2 as 0.03, or if it's from B3 as 0.02, respectively. Let's find the probability that an event or a pick was made and that pick is faulty. To find the probability that we took one of the products from a random supplier and that product was faulty. I'm sorry, please, the one with the hand up may speak. Okay, I'm sorry. So let's start with, let's check. So, Mr. Kayu. Okay, no, Mr. Emmanuel. Mr. Emmanuel.
Since I got, I don't know if I'm correct,
Yeah,
0.01.
0.01. Okay,
95.
Miss 0.0195. All right. Mr. Kayu. Okay, yeah, Mr. Kayu, please, what is,
I
have
I
you
also
worked
got
it?
195.
Oh, okay. And Mr. Freeman, okay, Mr. Freeman says thumbs up. So I guess he also got the same answer. Okay, so since we all got the same answer across board, then it's either we are all correct or all wrong. So let's test that first. So taking into account what we have been given so far, there are three separate events, and it says that three suppliers, they are all supplying products. One is B1, he supplies 40% of the parts. B2 supplies 35% of it, and then B3 supplies 25% of it. So it means if we check the supply or the supply, whatever, supply rate or supplies, some of it comes from B1. So 40% comes from B1, so 0.04. 0.4, sorry, comes from B1. And also from B2, 0.35. And then we also have B3. B3 supplies 25%, which is 0.25. Probability trees actually help you to visualize it clearly and then work easier, especially when you're applying Bayes theorem, which we'll be doing soon. So I might as well start using them now so that when you are working, you may also diversify the way you use your methods. I am just doing this so that you will be able to like also do it maybe when needed. It doesn't mean that you have to use it. It's just that you can use it. So now it says that from machine B1, we produce defective products. So from B1, the defective products we produce are, there's a 0.01% that the product is defective, right? So then this is from B1, defective from B1. And then it means there's a chance of it not being defective. So let's say not defective, D bar. This will be if there is a 0.01% chance, then it means the rest of it is going to be what do we call it? Perfectly fine, right? So that will be there is a 0.99% chance that the products from this side are fine. These are not values we are using in this question, by the way. As I said, I'm just demonstrating the probability tree so that you may be able to use it when a question is so complicated that it has to be represented visually before it can be solved. Okay, so now in D2, we have the, what do we call it? Defective probability of 0.03. So 0.03. That's defective. And then we have the non-defective probability of what? Since it's 0.03, then that's going to be 0.97. So we are just subtracting it from 1, since the total probability is 1 in each count, right? That's why I'm getting the values 0.97 and whatnot. And finally, for the next side, the defective and non-defective, the probability of it being defective from B3 is 0.02. The probability of it not being defective in here, if it's 0.02, then the rest of it will be 0.98, right? So this is a visual representation of what the probabilities look like. With this, we can now solve, or even without this, we could have even solved because it was easier. It looks like I'm making a small problem bigger, but please bear with me, just so that you'll know how to use the probability trees as well. So now what we are interested in now is the probability of picking a ball, a defective product from B1, that will be 0.04 times 0.01. You find that on your calculator. And the probability of picking a defective product from B2, that will be the defective, that's 0.03 times 0.35. So please punch that as well. And then finally, the probability of it being defective coming from B3, that is going to be 0.02 times 0.05. The reason why we are ignoring the non-defective sides is the question didn't mention anything about correct product. It was just interested in the defective ones. What this means is that a question can be given to you and they may ask you, what is the probability of picking a product that is not defective from a given factory? There are two ways you can do that. You can find the defective side and then subtract it from 1. You remember the complement rule, property 1. Or you may actually use these parameters here. So you can take the probability that it is coming from factory 1 and it is not defective. That's the 0.99 if the question asks for that. But this question didn't. You combine that with probability of it not being defective coming from machine 2. That will be probability of picking machine 2, 0.35 times probability of it not being defective coming from machine 2, 0.97. And you do same for the third side. Probability of it not being defective, but this time coming from machine 3. You multiply that. Yes, Mr. Joshua Anand.
Sir, please, why didn't you do the same thing for the previous question?
The 3.
Yeah, the 3, because I'm saying not defective, but the previous one we didn't do any not defective over there.
Okay. Sorry. Let me explain. I was saying that this question has not asked us for not defective. It hasn't. Okay. It has only asked us for defective. I am just saying that questions may ask. I am not saying this question has. Okay. This question has not asked for that. However, we may be asked in a different question, or maybe the questions we will come across. Remember, we're preparing for an exam, so we are looking at both sides of the coin. The questions we may come across may say that let's find the probability of picking a product that is actually not defective. Well, in that instance, we will need the parameters for the not defective probability. And that is what the tree diagram is for. It outlines both sides of each probability as well. So then in case we are asked, then we will need these parameters. However, we were not asked, so we don't need them. So Mr. Joshua, I am not giving an alternate, I am not giving a different explanation to it. No, I'm just telling more about it. Okay, so there is nothing has changed. Basically, nothing has changed. Why we are doing not defective here is if you are doing the tree, you have to express both sides of every probability. And that's why I'm expressing the side that is defective and the side that is not defective. However, in this question, we will not even use the probability of it being not defective. So sorry if I confuse you or something, but then please, it's a must. You must know it, okay? Okay, so now please, when you did the punching, what did you get? What was 0.04 times 0.01? 0.4 times 0.01. Okay, that's 4 times 1 is 4, and then the point jumps 3 times, right? So that will be 0.0. Is that 0.04? Yeah. Am I right? When you do 0.4 times 0.01, do you get 0.004? Hello?
Yeah, it's correct.
All right. Okay, and then the next one, if we do
Yeah, it's correct.
0.35,
It's correct, sir.
oh, okay, 0.35 times 0.03, what does that give us? So 35 times 3 is 105.
0.0105.
0.0105.
0.0105.
All right. And finally, we add that to the probability of it coming from machine 3, which will be 0.25 times 0.02, so 50, 0.005, right? Is that right?
Yes, please. It's right.
Or 0.005. Is this way, right? Yes, 0.0005. So now when we do the addition, what do we get? So please sum them up and let's see if the answer here is what we are looking for. Then we are good to go. Are we summing it up? Should I pull out my calculator as well? Let me do that. Okay.
Yes, it's correct,
So,
sir.
all right, 0.04 plus 0.0105 plus 0.0005. And our answer is 0.051.
Yeah. Hello, sir.
Yeah,
Sir, please.
yeah, hello.
The last one is 0.0. Yeah, sir, please. The last one is 0.05. 0.005.
Okay. Yeah, the last one is 0.005.
Yes.
Are you certain? When you do 0.25 times 0.02, it should be 0.0005. That's 5 times 10 raised to the power negative 4, right?
If we add them, we won't get the 0.0195.
Yeah, the 0.0195 was the answers that were given by
Okay.
those who attempted it here. So I'm implying that when you multiply 0.25 by 0.02, you get 0.0005. So then
Okay.
I believe that the fault to the answer came from the fact that maybe they might have written 0.005 instead of 0005. And that little mess up has caused the problem. So the correct answer should be 0.004, add that to 0.0105, and add that to 0.0005. And then what does that give us? 0.015. So the correct answer is 0.015. So Mr. Emmanuel, Mr. Kayum, Mr. Freeman, I'd like you to share what the mistake was with your working so that, yeah, Mr. Freeman, please.
So please, can we clear the diagram and everything, and then let's
And
solve
do
it
the
using
working.
the
Yeah.
formula line, because let's try that and let's see.
All right. So perhaps I'm the one who is making it wrong. Okay, let's check that. That might be true. Yeah, what have I done? Wow. Come in and give me a second. All right, here we are. Okay. All right. So let's use the formulas to do the working and see if we are on track or if we are drifting away. So let's start with the first side of it. The probability of picking a defective product, that's the probability of picking a product D, which is defective, is going to be equal to probability of picking a defective product from B1, which will be probability of picking B1 40% times probability of picking a defective product given that is coming from B1, like this. So that will be 0.4, that's for 40%, multiplied by 0.01. 0.01, like this. We combine that with the probability of picking a defective product given that it comes from B2. So that will be probability of picking B2, 0.35, or in other words, 35%, right? And then we multiply that by probability of picking a defective product now, given that it comes from B2, which is 0.03. So 0.03. And then we move to the next side of it. Add that to the probability of picking a defective product, but this time from machine 3. That's going to be probability of picking machine 3 first, which is 25%, so 0.25, 0.25, like so. And we multiply that by the probability of a defective product coming from that side, which will be 0.02. Combine these three. So let's do the multiplication step by step. So what does 0.4 give us times 0.01? 0.4 times 0.01. I have 4 times 10 raised to the power negative 3, which is the same as 0.004. So that's 0.004. We combine that with 0.35 times 3. So let's just punch so that we can be sure. Times 3. And that is, wow, 0.03. Good. 0.03. Good. So that's 0.0105. So 0.0105. And we finally, yeah. Yes. Hello.
Yeah, I think the answer will be
Yes,
what we
sir.
said.
You know.
The lady, please, I can't hear you. Sorry.
Get it now.
Mm.
I see
Mr.
what
And
Mr.
so
Freeman.
can you do here with the
Elementary
the
Yeah,
0.5 to 0.0?
Please,
The second one.
please,
The
let's.
second one is 0.015.
I'm getting the same answer.
Yeah, getting
Okay.
0.0. No. Please. One by one, one by one. Let's start with the lady. The lady, you were saying something, please.
Sir, please, I didn't see the 3 there. I thought it was 0.5 with the B section, no?
Oh, yeah, okay. Yeah, 0.35. Sorry. Yeah, the space is small, but it's 0.3. There's the 3, and there's the 5.
Yeah.
All right, okay. Mr. Freeman, you were saying that you still got the same answer. Eh? Okay, let's
I
let's
see where
land
my
it.
mistake was from.
Oh, okay. All right.
I see where my mistake was from.
Then the next one, 0.25 times 0.04. And what does that give us when we punch it? So 0.25 times 0.0.
0.005.
Yeah, 0.004. That's correct. 0.00. Let me see that.
5.
Okay, yes. So that will be 0.005. So 0.00. Oh, I see. So in the first question, we were writing one too many zeros. I was writing 0.00005. So then that is a miscalculation, right? So instead of writing 0.005, I was actually writing 0.00005. And that was wrong.
So the answer is correct, sir.
So yeah, so let's see that. So when you punch this, please, what do you get?
0.0.
0.0195.
Okay, so then Mr. Freeman, Mr. Venix, I and the whole world owe you an apology. You were right. I'm sorry. So then 0.0195. 0.0195. Okay, I'm glad. So it looks like we have understood the lesson so much that you can actually get it right, and then you can stand by your answer. That's great. Thank you for pointing this out. So then the problem was with the slip up I did with that small zero. And you see, that is big. And this is why whenever you are doing workings, you should always double check your answers. If they hadn't pointed this out, this would mean that we would have carried on without ever seeing this. And this can 100% happen in an examination. So when we are working in exam, for safety's sake, cross-check your exam, even work separately twice if you have enough time. It's a word of advice. Okay, let's move on. All right. So now let's look at the next example. So then there will be 5 examples on the total probability, and then there are 5 on Bayes' theorem. I have a feeling we will not get time to do Bayes' theorem because it's already 8:43. But then if we learn total probability today, then our next lesson, that will be 2 days from now, after you have done 2 sessions of the cons, concerning Bayes' theorem is going to be very, very simple. Okay? So there is no need to panic or worry. It's simple. All right, let's look at the next example. So now it says a commuter uses 3 routes to get to work. So now the person is going to work. Whenever he is going, he passes at 3 different places. When the person passes on route 1, he uses it 50% of the time. Route 2, he uses it 30% of the time. And then route 3, 20% of his time. Now, as he's on this route, the probability of arriving late, provided that he's on route 1, is 0.12. The probability of arriving late, provided that he uses route 2, is 0.20. And the probability that he arrives late, provided that he uses route 3, is 0.05. We are supposed to find the probability that the commuter, that's the person, is late on a randomly chosen day. So then we are finding the probability that he is late, but we are not specifying which of the roads he chose to use. So what's the probability that he's late? It means you have to know the probability of him being late on all 3 roads, and then you combine them. So then I'll leave that to you as well. Try your hands on this, and then we work it together. Yes, Mr. Kayu, let's hear you.
I got 0.13.
0.13. Okay, that's great. Yes.
Hello, Mr. Wilson.
Yeah. Yes, please.
I had 0.13.
Okay,
Yeah, I had
0.13. Okay, so Auntie Abigail, 0.13, Brad Joshua, 0.13, and then Brad Kayu, 0.13. Okay, so I guess the correct answer is 0.13. So then let's check that. So we just take the probability of what do we call it? Taking route 1, multiply that by the probability of being late, given that you chose route 1. And you add that to the probability of taking route 2, multiply that by the probability of being late, given that you took route 2. And you add that to the probability of root 3 multiplied by the probability of you being late, given that it was root 3. And yes, I have found this on my calculator as well. And the correct answer will be 0.13. So what we are basically doing is doing this 50%, that's 0.5 times 0.12. And then we do 30%, which is 0.3 times 0.2. And finally, we do 20%, which is 0.2, and multiply that by 0.05. And then we end up with 0.13 when we add all 3 products together. All right. So let's move on to the next and final example. So then you see, I have come to realize, and then through my experience with the little experience I have teaching maths, that sometimes it just takes constantly solving examples to understand the concepts. And then I will be displaying the formula across screens, just like this, so that with every spot, it sticks. Now, I believe that the statistics, I think the man mentioned that there will be objectives, but please remind me, did he also say there will be subjectives?
Yeah, he
Yes,
even mentioned
yes. He
some
said there will be
some
24 subjects and we will choose 2.
Okay, so then given that assumption, then it means we will also need to, write and apply these formulas. I don't know if the formula writing will be a requirement because in last semester's exam, when we took our final exams, most of the questions I solved without stating formulas. When then the results came out, I had passed successfully. This means that I doubt I lost any marks for not stating formula. So then there is a fine possibility that you will not either. That being said, Mr. Ezekiel is different from Mr. Senator Gaduso. Keep that too in mind. Anyway, yes, let's look at the last example. Okay. Okay, Mr. Joshua. Mr. Joshua. Is it Joshua N or JN? What does JN stand for? Intereba. Oh, Mr. Intereba, long time. Oh, Mr. Intereba, please, let's hear you.
Good evening.
Good evening,
Yeah,
sir.
yeah, please, I want to talk about the formula issue.
Yeah.
Yeah, the little I have to contribute is that I see the formula is necessary.
Okay.
Most of the examiners, once the formula is there, they will always look at the final answers. So when they see that you
Wow.
put the formula well, so they will look at the final answer. Sometimes they will not even go through the work, since the formula is very correctly stated. So that is how most of the math teachers used to mark, because they don't have enough time to mark. So once you are given a formula, they assume that you know what you are doing. You understand?
Yes, sir.
So I think formula and data is part of math. Formula and data is part
Okay.
of the when it comes to mathematics solving. So that's what I have to say.
Thank you, Mr. Intereba. I believe this is the best advice that someone could ever give you. Just state the formula. So as he has said, given that these people are marking a lot of papers, then you can only assume that if they see correct formula, they assume the person knows what they are doing. Therefore, if the person arrives at the correct answer, they might not even bother to check the working, and they will just mark it correct. And he is right to say so. I believe, because yeah, my colleague math teachers will agree with this if you're marking a lot of papers. So I believe he is right. So keep that in mind. Mr. Ezekiel always said, you stating formula never mattered. Just do the right working and then come by your answer. However, as he said, generally, math teachers want to see what you know so that they can easily mark the answer correct without having to go through the trouble of doing all the activities. Yes, Mr. Joshua, let's hear you.
Oh, the answer.
Hey, you were working. Okay. Yes, what's the answer?
0.0635.
0.0635. 0.0635. Okay. Don't forgive me for my handwriting, okay? I won't say it's because I'm writing on the machine screen. That's why. In real life, my handwriting is still bad. Just forgive me for my handwriting if you can see it clearly. So this is 0.0635. Okay. Right. So back to the question. Thank you for drawing us back into the class. Is there anyone else who has worked it? And what is your answer if you have? Mr. Samuel, you are requesting control. Why you want to control my screen? Mr. Samuel, please, if you want to speak, you may go ahead and speak. Please, are we working or I should just go ahead? Because this is silent. Are we working?
Yes, we are working.
Right. Thank you for that reassurance. Mr. Freeman, let's hear you, please.
Yeah, I got the same answer.
0.0635. Okay. And then
Yeah,
Auntie Abigail.
yeah, same answer.
Oh, okay. Okay. 0.0635. So let's cross-check that. So then from the question, the probabilities we've been given are 0.25 from a region B1. So the probability of you getting a sample from B1 is 0.25. And the probability of the sample being defective is 0.05. Now, from a region B2, the probability of picking the sample from there is 0.4. Probability of it being defective is 0.03. Probability of picking it from B3 is 0.2. And the probability of it being defective is 0.12, as you can see here. And then finally, probability of it coming from B4 is 0.515, and the probability of it being defective is 0.05. So with this, we can now compute the total probability by multiplying them and combining. So let's do that and see if our answers are correct. So 0.25 times 0.08, add that to 0.03 times 0.40, add that to 0.12 times 0.20, and finally add that to 0.15 times 0.05. And that gives us 0.0635. So congratulations, everyone. Your answers are perfectly correct. Your answers are perfectly correct. So now we have come to the end of our session. However, before you go, I want you to try one more question. The question is this. It says, what's the overall probability that a random sample tests positive? You have just calculated that. Now, what is the overall probability that a random sample tests not positive? What's the total probability that a random sample tests not positive? Yes, Mr. Freeman, let's hear you.
0.9365.
Okay, 0.9365. Mr. Joshua or Mr. Abigail. Hey, Auntie Abigail. Sorry, Madam Abigail.
Same
I'm
answer,
sorry.
please. 4.9.
Same answer.
Yeah,
Three,
65.
Same
six,
answer.
five. Oh, okay. Oh, all right. Charlie, you guys are too much. So I see you applied the property one, and then it has brought the answer very fast. 0.9365. Thank you very much. So then this one shows you something. In case you are given a question and the question gives you parameters for, like this one, gives you parameters for positive test results and asks you for negative test results, the probability. What this means is you can see they've not given you the probability of a negative test result. Therefore, just find a positive test result and then subtract that from 1 using property 1, and then you get the answer. Or inversely, you may find the mirror probabilities of all these probabilities. So for example, if it tests positive from machine B4 at a rate of 0.05, then it means it tests negative at a rate of 1 minus 0.05, which will be 0.95. That will be a waste of time because you will have to do it for all these events. So you subtract these two from 1 to find the probability that is negative. And you do the same thing for this guy to find the probability that is negative. And when you're done, you put those probabilities into the formula, you sum them up and you get the answer. So it's either that or you can do what you just did, find the probability that they are actually positive and then apply rule number 1. My name is Prince Nanada Kosen. Good evening, everyone, and then goodbye, good night. It has been a great section. Thank you for being with us throughout. I'm going to put questions that I directly lifted from the questions that I've gathered so far that are concerning total probability. There are a few, they are just far too few. And then I'll put them on the platform, about 1 or 2 or 3, and then you will work them out. Total probability is really used in Bayes' theorem. So it is almost never used alone, like in instances like this. Therefore, Bayes' theorem is where you will truly need it. So good night, everyone. Have a great night. You'll see the questions on the platform soon. Thank you for your time. Goodbye. Ima, stop dropping hearts. No, Didi, stop dropping hearts.